Hi, this is Ari Everett for CSC120, fall of 2023 for Professor Cody Anderson's class. This is a demo for quiz 5. I used the quiz as the basis of the material to demonstrate and changed some things to do different problems than the original quiz and answer problem. So these topics include from topics 8 in weeks 10 and some of 11. We cover sequential circuits and the basics foundations of analyzing those circuits, specifically with flip-flops. Let's go through problem 1 here. So it asks us to make this timing diagram. What I did was switch J and K and pre and clear opposite from what the quiz was. So it would have made different outputs for Q and Q naught here. I used a straight edge to show where the positive edges are. It's still a positive edge circuit and flip-flop, and Q outputs are labeled here. I created a little timing diagram, but this is called a characteristic table and not a transition table to help me walk through the JK flip-flop. And the naming conventions for each of those combinations of J and K are right here, as the clock's edge is positive. So we can see every positive edge, it will do that. We see that J is on the 0 side down here, and then K is on the high side this first time, and we have to wait for the positive edge of the clock, and that's when we reset. So we stay reset as the initial instruction says, reset, we're low here, and then high for the not. And then once, let's see, the next instructions are low and low, which is no change. So on the next edge, that's still low and high here for the outputs. And the next one is J high and K low, so 1 and 0 is set as we see down here, so that sets it to 1 for the output, and the not output goes to the opposite of that. It goes back, stays high and stays high here, so it stays set until we have an asynchronous active low here, which will immediately bring it down to low and the opposite high. Even though it comes back up, it's asynchronous, and we want to match back up with the next clock edge, so that's why it doesn't go back to high like it was previously. It stays low until the next set of instructions, which are J high and still K low. So it goes back to that set that it was. And this last one is high and high, which is a toggle from our table, and that is output. For problem 2, you make the characteristic table for a T negative edge with a clear active low initially, but I made this a D positive edge, still with a clear active low. So here's the characteristic table. The output follows what D is, so D0. So D plus the next state of 0 would be a reset, and then 1, it would follow, the next state would be 1, it follows it. The opposite is the opposite of that, obviously. Name is, that's the set, and clear is still active, or not active, high as the not right here. And then once clear is 0 at an active low, I just called that the clear state, and it doesn't matter what the current state is or what D is, it will always output a 0. I will correct this right here. It's not a don't care, it is actually okay. And then we'll go to target A, the last problem here. First question was, is this a Mealy or Moore machine? So this is a Mealy machine because there's no direct input to the output directly from the inputs. So X does not go directly into Z. The only input into Z output is the Q naught 1 here. And the things I did to change this around is I made every single AND gate to an OR gate here. You can see. So first we derived the Boolean equations. For example, J1, you can trace this back here. This goes back to this OR gate, and then branches, it goes to the original X, so you put an X in there, or the Q0. And I rinse and repeat that for the remainder of the equations here. The Z is maybe the only unique one where we have a very simple output of the flip-flop 1, which was the Q1 naught. So we follow the design steps to analyze similar to what we design, and instead of step 5, you kind of have step 5 here initially. So let's loop back around to reverse engineer that design process by analyzing it. So once you have the Boolean equations, you can do the other steps here, which was picking your flip-flops and create the transition table here. So what I created was, since it's a 2-bit circuit, 2 flip-flops, 1 bit each, so 2-bit, I created state names for the states of each of those two bits. It could be 0, 0, 0, 1, 1, 0, or 1, 1. And then for each of those groupings, I named them A, B, C, and D. Input is what we input into it. So I put a characteristic table here, a reminder of my JK table to build out this table here. So let's bring you through that example. So for example, A, Q1 and Q0 is 0 and 0. Then the X input is 0. I use the binary table all outcomes shortcut here. So 0, 1, 0, 1, 0, 1, etc. And here you do every other 0, 0, 1, 1, and then repeat. And then this one you do 4 times, 0, 0, 0, 0. So for the flip-flop inputs, we get this 0, J1, from the answer of this Boolean equation. So J1, when X or Q0, what is that output? So I can look right here. X is 0 and Q0 is 0, then that is also 0. And then I fill that with these two. I fill out this equal sign. For K1, it was a bit more difficult. I had to write this one out. Used all three of these, but remember it was the Q not 0 to build this. The remainder were fairly easy, just like the first one. You just look at the J and K are actually the same. You just look at the X and Q1. So Q1 is 0 and X is 0, and they're ORed together. So 0 or 0 is 0. And here 0 or 1 is 1. And for the next state here, which is highlighted by pink highlighter, you get the next state of Q1, and then Q1 plus signifies the next state, after you input an input of JK01 to that flip-flop. So what does Q1 become? This is the starting point, 0. JK, our 0, 1, which we know from our characteristic table is down here, is reset. So that goes to 0, but it's already 0, so it stays at 0. Next one is a good example of how it changes. So it starts at 0. It is 1, 1, which we know to be toggle. So that changes 0 to 1. Rinse and repeat for the rest of these columns here. Next is the Z output. Again, you get this from the Boolean equation. Okay, in the final column here, the next state name, which we get after the input and memory changes, we look at the next state Qs, Q1 and Q0, and match them to the state name from over here. So we can see this grouping, A, is 0, 0. So over here, Q1 and Q0 in the next state are 0, 0, so I put A. We see that this is 1 and 1. We search down here, and we see 1 and 1 is the D grouping, so we put D, and so on. Next, we create the state diagram. Some shortcuts we found from the presentation are there's 8 rows, so we know there'll be 8 arrows. There are 4 different state names, so that we create nodes for each of those, and we put the matching binary number next to them in their node, just as a reminder of what they are. And then we use these black boxes that I've made up here to remind us what to look at from the transition and state table here. How we draw arrows from each of them in the state diagram is A, we have a loopback 0 here. We can see that A, input 0, and then we changed it to A. Next example is A, we input 1, and it changed to D. So we'll draw this arrow 1 to D. And we rinse and repeat for the rest of it, and we get this here. Finally, we would implement test. I called it analyze here. As from the original question for describing this, it is a Mealy circuit because no input goes directly to output. Some things and patterns we discern from it. If you start at reset or 0, right here, which is 0, 0, then you stay in this kind of channel. And if you start at 1, then you would stay in this B and C channel. So my discern of this was that it could be some sort of switch or mechanism with rules that if you start in a certain state or a static state, you would stay in only these 2 lanes. Like if you click chocolate ice cream, you're only allowed to get 1 or 2 scoops of it. If you pick vanilla, you can get 3 or 4 scoops of it. That's it. Thank you.